This conference will now be recorded.
Yeah, please go ahead.
So should I share screen or share applications in a share menu?
Whatever works for you. I think sharing screen is okay, and if we are in the presentation
If
mode,
I click share screen, I don't see okay, I only
yeah,
see a very small
yeah,
screen.
we don't. I think you're not sharing the right screen. You may have many windows open. Yeah, there you are. Yeah, click on that one and make it full screen, please.
Full screen, how? I don't see
the top, the top right.
नहीं कुछ भी नहीं मैं टाइम ये मैं जल्दी बताओ यार
जो सबसे
The
कम
top
टाइम लगे
right. Yep, next to the
Yeah.
X.
No.
बिना प्याज के बना दो आधी प्याज से बना दो मैं जा नहीं सकता अभी भाई
Could everybody please go on mute? Thank you.
And
go in the presentation mode. Click on the bottom. See the presentation mode button right at the bottom.
I only see a very small screen on my.
Right. So go to the presentation mode at the bottom of the screen. On the right where the 4 boxes are.
I can't even see it.
Okay. Go back to PowerPoint, please. You're fine.
I don't know how to.
No, it's okay. David, it's okay. Just go to PowerPoint at the bottom, where all the icons are for different presentations. Yep, click there. Perfect. And in that, you just take your mouse at the bottom and where the projector button is.
But I can't. The problem is I can't see my. I only see very small screen.
Right. You have to make this screen bigger. If I'm seeing the same screen you are seeing, there is a red ribbon on the top, and the ribbon on the top and the second button from the top right that will make your screen bigger. You see the
okay. I just can't see. Okay.
No problem.
Yeah, the problem is.
And also press F5 on your keyboard.
There you go. Yeah, that would be helpful. Yeah.
The problem is my screen is very tiny. I have 2 screens. One is I see all the attendees, but the presentation screen is tiny. Toggle the full screen, top right.
Do you see a ribbon on the top which is red in color or sort of orange in color, and orange in my screen?
No, I don't see it.
Oh, you don't see it. And can you go in the presentation mode by clicking on the projector button? Yeah, right here. That's where I am. Yep, there you go. Is that better?
Yeah, you see my full screen, right?
We do.
Okay. Then I can continue.
Then we can get started. All right, David, over to you.
Yeah, today's topic is of the ORV3 high power version power system. I'll give you a technical overview on this new project. Okay. So, first, what is ORV3? We call it high power rack, ORV3-HPR. ORV3 high power rack is the next generation of ORV3 rack and power solution, delivering a higher rack power that is driven by the next generation AI systems in a data center. Okay, so there I made 2 tables, compare the rating of the existing ORV3 and the ORV3 high power version. You can see the rack level power, including the BBU recharge power. For ORV3 in the N5+1 configuration, we get 15 kilowatts. In the 11+1 configuration, 2 shelves, 2+2, which we have 33 kilowatts with 11+1 redundancy. the size, including BBU and PSU, is 6 OU. So for the high power version, we're going to increase the PSU module power to 5.5 kilowatts per PSU. Same shelf form factor, same space in the rack. So in the 1+1 configuration, we get 27.5 kilowatts. And in the 11+1 configuration, we get 60.5 kilowatts. In the 17+1, 3 shelves, we got 93.5 kilowatts. For the BBU backup time, we have 2 flavors. Same design. For 20, if people want longer backup time, 4 minutes, you get 4 kilowatts per BBU module. But the same design can support 5.5 kilowatts for 90 seconds. Okay. Next page. So why is it needed? Our next generation AI system, we are seeing up to 80 kilowatts per rack. And next generation compute racks, we are seeing in the range above 15 kilowatts, up to 27.5 kilowatts per rack. Originally, if we are using ORV3, we need 2+2. But if we use HPR, we only need 1+1 for the general computing racks. And we can fully utilize the new data center power capacity per rack space in terms of cooling and the electrical design. We have enhanced our cooling and the upstream electrical design to support more power per rack, basically. Okay, what are the major changes compared to ORV3? Per PSU, the power is increased from 3 kilowatts to 5.5 kilowatts. And BBU, same thing, 3 kilowatts to 5.5 kilowatts. For those users needed 4 minutes, the power is increased from 3 kilowatts to 4 kilowatts. And the bus bar used to be 33 kilowatts. Now it needs to support 80 kilowatts. It's more than doubled. And PSU BBU shelf bus bar clip used to be 18 kilowatts per shelf in the 6+0 configuration. Now it needs to be 700 amps to support 6 5.5 kilowatt power supplies. The tab box is on the data center AC busway. It has circuit breakers inside to support the rack, to provide the feed of the AC power to the rack. So originally we have 220 amps tab box max. Now for 33 kilowatts, we're gonna have 3 30 amps tab box for 93.5 kilowatts, 3 shelves. AC whips used to be up to 4 per rack. Now we need up to 6 per rack for 93.5 kilowatts per rack. Okay, no change. The architecture, no change. The power, we have 48 power zone, single power zone, flexible and independent shelf position means you can plug in the power shelf anywhere in the rack, BBU shelf anywhere in the rack. And PSU BBU shelf rack dimensions, no change. The Modbus communication, no change. Major change of PSU or rectifier. The output power increased. We increased the PSU length by 120 millimeter to 640 millimeter. The peak power, we enhanced the peak power performance. we target 50 milliseconds, 136%, 400 microseconds, 160. This is based on the GPU spec. Okay. Compared to ORV3, 50 milliseconds, we can get only like 110%. We eliminated the 3-volt gap between the PSU and BBU output voltage by implementing a new control method, which is using an AC loss signal. It's simple and reliable. Okay, has a lot of benefits. I'll explain later how the new method works. We incorporated, this is another major change. We incorporate the busbar clip over temperature monitoring. Basically, we put 2 sensors on the shelf busbar clip plus and minus contact. So they can report alarm, and we can also control fan speed based on these signals. And so we can avoid the busbar clip over temperature. Upper voltage setting, now we have a narrow range unified for BBU and PSU. It has a 1-volt droop from 0% to 100%. Remember the ORV3 has 0.5-volt droop. So the 1-volt droop, the larger droop will help us for transient mode current sharing. Okay. And the droop extend to the peak load. So what are the changes for the PSU shelf? Up power 18 kilowatts to 33 kilowatts per shelf. And we now support 3 shelves in parallel to get a total output 93.5 kilowatts per rack, 3 OU space. New busbar clip rated 700 amps is under development. And we have some misters added for monitoring and protection. Each shelf has dual 30 amps input for North America. It's derated to 24 amps. And it has a dual 32 amps input for Europe. And these 2 versions electrically can share the same design. Okay. Just labeling difference. Major changes of BBU. BBU max power increased accordingly from 3 kilowatts to 5.5 kilowatt. BBU length increased by 30 millimeter compared to ORV3, but the shelf size stays the same. Backup time, two choice. The backup time is programmable through the Modbus and enhance the peak load performance according to GPU requirement. Eliminated the 3-volt gap, and last bullet, same output voltage as PSU. So it's beneficial also for the downstream DC-DC designers. They have a narrower input range. Major changes of PPU shelf. Maximum output power increase from 18 kilowatts to 33 kilowatts. Backup time, two options. New busbar clip is needed. We decided to use the same clip as PSU, although the BBU has only a very short time power heating. The PSU and the BBU shelf can support 3 shelves in parallel for close to 100 kilowatts per rack. Okay, this page I explain the new control method from AC to BBU transition during AC loss. So original design ORV3 will lower the busbar voltage by 3 volt during the hold up time for BBU to take over. But in a new design, we have an interconnection cable between the PSU and BBU, actually 2 cables. 2 cables. So each PSU shelf has 2 by 2 4-pin connector. Okay. And each 4-pin connector has 3 AC loss signals of 3 power supplies. And each BBU has 2 AC loss input signals. For example, BBU1 takes the AC loss signal from PSU1 and PSU2. BBU2 takes AC loss signal from PSU2 and PSU3. So only when both AC loss signals are true for a BBU, the BBU will start to discharge. And in the meantime, it will pull the sync star signal load. Sync star signal is the signal connecting all the BBUs together, including different shelves. And if one BBU get 2 active AC loss signal, it will start discharging all the BBUs in the rack. So that way, we can avoid a single cable disconnection. For example, you have a bad cable. Even only one cable works, you still can support the backup. The backup operation still works properly. If that also avoid a single fault. Let's say if one PSU has a false alarm of AC loss, it will not trigger BBU to discharge because any BBU needed 2 active signals to turn on the discharge. So what's the benefit for this change? So original design, we need to reserve pretty much 50% of the bulk cap energy for transition from during the hold up time from PSU to BBU. The new design, you can almost fully utilize the bulk cap energy for the peak load. And it's simple and reliable because the original design based on our experience during the dynamic load, peak dynamic load and AC on off, the 51 volt to 48 volt drop could be stretching to the PSU capability. The voltage undershoot could become a problem. Okay, it's very challenging. And the second is simple and reliable. Okay, we covered single fault and we covered redundancy. And it has a narrower output range, so which is beneficial for the downstream DC-DC converters. It provides more possibility to use the fixed ratio DC-DC converter. Okay, to support 3 shelves in parallel, we don't have enough address based on the original ORV3 design. So originally, the Modbus address only support 2 shelves in parallel. To solve the multiple shelves, 3 or more shelves in parallel operation, I modified the PMI circuit. So added 2 DIP selective switch, the small DIP switch in the PMI board. PMI is an open frame board. So when the ODM integrator, when they install the shelf into the rack based on the shelf position from the top, let's say the number 1 is the shelf from the top, they select the switch number 2, make it close. So default is open. Open means 1, close means 0 for 3 address pins. So 011 is the first shelf, 101 is the second shelf, 110 is the last shelf. And switch 1 is for backward compatibility with ORV3. If switch 1 is closed, switch 2 is all open, then it becomes ORV3, it's PMI. But if switch 1 is open, you toggle the switch 2, you can support up to 8 shelves in the DC chain. for communication. Okay. Oh, lost. Okay, that's all my presentation for today. Now is the section for Q&A.
Thank you, David. I think that was very informative, and we got to know how you are communicating between BBUs and BBUs and the PSUs, and also, and how this 3-volt difference is. I think this is an interesting change as well. So
Right.
I guess with that, we will open the floor to questions. Anyone has questions, please go ahead.
Go ahead and start. This is David Moore with Meta, with NVIDIA for questions for David.
Yes.
The thermistors that you're putting in the bar clip connectors, are those
Yes.
only on the power shelf, or will it be on the gear connectors as well?
So far, it's only on the power shelf. The power shelf connector is up to 700 amps. It's quite large current. The IT gear connector, they have a smaller current, 150 amps, if I remember correctly. So far we don't have but they can use the same method it's quite simple. It's not very hard. And you already have all the major connector vendors. They already have the solution, and we have the samples. We unified the thermistor as a 10K NTC thermistor. It's cheap and reliable.
Are you going to use that for, I'll say, just information only, or will it be part of safety to trigger over temperature protection?
Yeah, the major intention is for safety protection, because original design, we don't know if the connector overheating. There's no information of the connector temperature. So if there's a bad contact, then some thermal event may happen. So with this thermistor, the last thing we can do is to turn off the power shelf by itself if the temperature is over a threshold. We can set multiple levels of protection. First level, we get an alarm, because this data, this temperature will be available through the Modbus to the rack monitor. So the rack monitor can decide to create an alarm before PSU shutting down. Also, this temperature can be used for fan speed control of the PSUs. We can increase the fan speed when the busbar clip running hot.
Okay. Yeah, I'd be interested in understanding, the details for, your use with the PMI versus intelligent controller or power supply. So there's lots of options we could do with this thing.
Yeah.
My other question would be, how many power shelves and BBUs would your AC loss signal support? Can it be daisy chained, or is it limited in number of shelves?
That's a good question. Let's assume I should make another drawing. If we have 3 shelves, imagine we have 3 shelves of BBU, 3 shelves of PSU, and we can just simply connect PSU shelf 1 to BBU shelf 1, PSU shelf 2 to BBU shelf 2, and PSU shelf 3 to BBU shelf 3. So the BBU shelves, each individual BBU, they are daisy chained. They have a sync start low signal bus. So this signal bus is daisy chained to each of the BBU shelf. So any one of the BBU in the shelf set the sync start low, it can turn on all the BBUs in the rack.
Okay.
Yeah.
Thank you.
David, it's Harry here. We see, and I was a little bit surprised, and pleasantly surprised to see that we are approaching 100 kilowatt in the total rack power. Is that
Yeah.
correct? In 17
Yes.
plus 1? I mean, I guess this is the first I've seen. I mean, yeah, there you are, 93.5, almost 100 kilowatts. I mean, this is in the air cooling. Do you believe we are reaching the limit in terms
Yeah.
of the thermals you have seen, or what are your thoughts on that?
Yeah. So as I mentioned earlier, our immediate need is 80 kilowatts. Like here, the first bullet. Our next generation AI system, we are seeing around 80 kilowatts per rack. So the immediate design target as the first stage is 80 kilowatts. That's mainly due to the limit of the bus bar, because we have a single bus bar in the rack. And the power supply itself is capable of 90, because we have 5.5 kilowatts module now. Original, my target was 5 kilowatts per PSU. Thanks for Dave Moore. In the previous presentation, he's asking for 5.5 kilowatts per PSU. So I decided to stretch a little bit further to 5.5 kilowatts. Then that gives us 93.5 kilowatts. So to achieve the rack level 93.5 kilowatts, first we need a solution for the bus bar. We also, of course, cooling is another problem, right? Rack level cooling. Liquid cooling is definitely needed. In the new data center, we already designed in the liquid cooling, but the capacity need to be evaluated to support 93.5 kilowatts. But when I design the power supply, I don't want to design barely enough, right? I need to reserve some space for the future, because to change the power supply design is not a simple thing. So 5.5 is almost the upper limit from the top power feed. You know, we have 24 amps per line. If you calculate based on 277 volt, that gives you about 5.5 kilowatts, a little bit more, close to 6 kilowatts. So the target is 80 kilowatts per rack, but for PSU design, it's 93.5 kilowatts per PS with 3 PSU shelves. It's capable. Okay.
Hey, David, one question. So you mentioned like there's a current limit due to the DC bus bar. Is that meaning the
Yes.
current density of the cross section, or is some other limitation?
Yeah, you basically just need more coppers, more cross-section area to carry the current. Because we are considering the one, that it doesn't mean we cannot support 93.5 kilowatts today. For 5.5 kilowatts, we are considering the worst case, which means you put all the 3 power shelves on the very top, and you have the loads pretty much on the bottom side. In that case, the bus bar cannot support 93.5. But if you put the PSU in the middle of the rack, then it's no problem. It's much easier because the power loss is 1/4. So right now we are working. Dimitri, you want to chime in on the bus bar design question? Are you there?
I thought I saw Dimitri.
Yeah, probably he's on mute.
Probably, yeah, that's.
Yeah, our mechanical engineer is working hard on to design the bus bar and the cleave and the thermistor. It's all their great job, you know.
No, I think we are, and I completely agree, David. Mechanicals, electrical, we are pushing technology. I think we are. Yeah, I know I'm pleasantly surprised to get close to 100 kilowatt, and this was, seemed like a very difficult to achieve target a while back. So, when you talked about just David, one more question on you mentioned liquid cooling. Can you shed? Is it those manifolds we have on the ORV3 rack, the high power racks? You are not talking immersion, right? You are just talking liquid assist, right? Like we've done in the past.
The first stage we have air assisted liquid
Right.
cooling with manifold and those kind of
Right.
things. Yeah, but for the new data centers, we're gonna have the pipes, right? Circulated.
Circulating, yes, exactly.
Facilitate liquid
Yeah.
cooling. Yeah.
Yeah, yeah.
Mm.
But
Which
not
increase,
immersion in the
power
cards in the
capacity a lot.
near term, right? Sorry, David, go ahead.
The next level of data center liquid cooling is facility level liquid cooling. The per rack power capacity is greatly increased.
Great, thank you.
Yeah.
Any other questions?
Yeah. So one more question. This is Wei from Tesla. So I saw you drop the DC bus line load voltage from 51 volts to 50 volts. Like, what's the reason for that change?
That's a good question. Originally the PSU setting is 51 volt at 0% load. I dropped by 1 volt. Original ORV3 PSU output is 48 volt at 0%. So there are 3 volt gap between. I decided to drop the PSU voltage by 1 volt and increase the BBU voltage by 2 volt and meet in the middle because I increased also the droop by 0.5 volt. So this number is flexible. I have a feature in the PSU and BBU design make this output voltage adjustable incrementally through a Modbus command. So we can, down the road of the project development, we can fine tune the voltage setting. Let's say, oh, the DC-DC designer may say, hey, can we have 49.5 instead of 50? Yes, that can be done. So I'm also trying to get the feedback from the downstream DC-DC designers. Which bus voltage do you prefer? 50, 49.5, 49, or what else? But they are looking for, it's how to say, to support 4-to-1 fixed ratio converter, their target output voltage is 12 volt plus minus 5%, including DC and ripple noise and AC transient. That's hard because if you have an uncontrolled DC-DC converter, although you have a tight range on the bus bar, I still imagine you have a long distance from the bus bar to the point of the load. To maintain the 5% tolerance, including load transient, even I have a tight input on even have a tight output range on the power shelf, it may not be able to satisfy the 5% target at the load because there's distribution loss, there's inductance, there's cabling, there is the DC-DC converter itself has some voltage drop, although it's fixed ratio 4-to-1, but there's voltage drop, IR loss, magnetic loss. So very likely they still cannot use the 4-to-1 fixed ratio if the plus minus 5% is hard requirement. And plus, the major power consumption is the GPU system. And David Moore knows better. The GPU system they don't care, they takes the 48 volt directly from the bus bar. So only a small portion, to my understanding, you can correct me, only a small portion of the system power need to be regulated to support like memories, 12 volt memories, fans, which need a tight regulation. For those things, they can use a regulated DC-DC converter. There's no much difference in terms of efficiency and cost.
Yeah, thanks for the details. Yeah, this is helpful.
Yeah. So this voltage, bottom line, this voltage is adjustable because we just started the projects, and we can still fine tune the voltage setting down the road, moving forward. Yeah. Okay. So the new generation greatly increased the power capability of the ORV3 within the same architecture. That's the main purpose, to get more power, because the AI system is asking more power. And we have to provide a power solution. There's no choice. The overall form factor is pretty much the same. Architecture is the same. Rack space.
Any other questions for David? If not, I have a question for David Moore. David, I know David Sun just mentioned, we are reaching like with 24 amps per line, we are approaching close to 5.5 kilowatt. Are you looking at this application at 230 volts / 240 volts or 277 as well? I'm just worried about more derating and the margin we have at the lower end of AC voltage.
Right. I base the 5.5 kilowatt ask on really it's a 60 amp input connector.
Okay, yeah, right.
Yeah, we've got customers, still at 208. The 230, 240 is really what NVIDIA pushes people towards. And that's where, in addition to what David Sun is asking, I'm looking at the input, the positronic Amphenol and others input connector to the power shelf and trying to get that one pushed up in current as well.
Yep, makes sense.
Yeah, for 230 volt, like Dave said, they need a special 60 amps input connector. So that the ORV3 HPR will be derated at 230 volt. For our Europe data centers, we have 32 amps input, and they are not derated. So 230 volt, 32 amps, you still get full power from the HPR. In North America, the 30 amps is derated by 80%. It's not enough for the full power.
Yep. I understand there is a lot of constraints and for people who work. That's why I need to bring out that question to understand the applications which people might be considering. Yep.
Okay.
We still have a few minutes. And David, I take it you have released all these specifications, all 4 of them, and they are available on the Rack and Power Wiki site.
Right.
Of course.
We already released the specs. We're gonna kick off the design.
Right.
Very soon. Yeah.
I just wanted to bring it to everyone's attention that somebody is looking for details of the specifications. They are available.
Yeah.
And so I guess if there are no more questions, we can conclude this meeting early. And like they say, I give 15 minutes back. So,
Sounds
and
good.
David, thank you so much. I think this was very informative, gave us really an insight into the future architecture and all the ins and outs and the challenges. Really appreciate it. Thank
Yeah,
you.
thank you.
Great
Can you
presentation. Thank you.
will stop my sharing? I don't know.
Yes, please. Yes.
You know,
Thank you, David.
yeah, I don't see where is the share button. Maybe you'll stop my.
When I stop, yeah, there you are. There you
Okay.
are.
Okay, good.
We are done. All right. Thanks, everyone.
Okay, thank you.
Thank you.
Bye-bye.
Bye.
Bye.